Okay, so for today, I was planning to do and again a bit more theoretical meeting, and on Thursday we will start doing programming, so that will be very practical from Thursday. But today I would like to speak about how can you install programs, or how do you have to install the bioinformatics software you will use. So what we will learn today is what's the difference between installation of a program on a graphical user interface, which you probably used to, so on a Windows, on a Mac, and how it is comparable to command line installing. Ooh, I'm hearing myself. Can you?
Yeah, I'm gonna switch up. Wait. Someone.
Can you mute people?
Yeah, I can mute.
Wow. What a power. Okay. So going back to our list, so you will learn what is dependency and why it is important. You will learn how you can provide the required environment for those applications you want to execute or you want to use as in your bioinformatics questions. And also, I will try to give you a few tips and hints why one is better than the other, or why one is worse than the other. So hopefully at the end of this course, you will be able to decide which installation path you would like to use. With my email. You will be able to compile a program from source code. I won't speak too much about compilation, but actually there is a very good video which I linked to the email. So that's about how you can compile programs, but I will speak about compilation. You will understand the significance of the running environment. I will speak the most about why the environment is important, what kind of different environment levels you have to care about. And hopefully you will be able to do some basic troubleshooting as well on installation and running errors. So installing a program for most of you, and also for most of the people, is just simply downloading an exe file or an MSI or a PKG or a DMG, depending on the platform you are working on. Download from a website, double click, and then follow the installation procedure, which is pushing the next buttons, reading the end user license agreement in full, of course. And that's all. And then you can use the program. In a Linux environment, it's usually very different. In bioinformatics is almost always different. So for a few software, for a few programs, even in Linux, you can follow this kind of procedure. You can just download a package and you can install it without knowing too much about what is happening in your computer. But this is not really true for small individually developed programs, what we usually use in bioinformatics. It is true, for example, if you want to install OpenOffice, which is the Office alternative, Microsoft Office alternative for Linux, you will probably just download an executable installer, which will do the installation for you, or the GIMP, which is a graphical program for Linux. So that can work for a few packages, but it's not really common in bioinformatics that you can install a software with the Linux own package manager. Blast is in that level, which you can actually install, for example, in Ubuntu Linux with the package manager. But Blast is one of the biggest bioinformatics the oldest or the most commonly used bioinformatics software at the moment. The next level is that you are just downloading an image, which will create a sub or a microenvironment in your computer. Everything is packed in, so you just actually log in or go into that sub environment, and you can do everything. And this is what Docker do. It creates a sub environment, and it's completely isolated from everything else. So even if you download two bioinformatics software that are using the same kind of environment in many perspectives, I will speak about this a bit later, then they have to re-include all these parts. So if there are two programs using SAMtools, which is a very common package you are using if you are working with next generation sequencing data, the SAMtools will be installed and included in these sub environments for each. They are not sharing SAMtools, so you have to install, or you have to provide enough storage space for both SAMtools installation in both sub-environments. The other type, which is also very common, actually, the Docker is quite common in bioinformatics, but the one which is even more common is the Conda type installation, which is also a kind of environment or sub-environment creation. But in this case, if you are installing two different software with Conda and they are overlapping in their environment, then they will share that environment, which can actually cause a few problems. We will speak about this again a bit later. And the most time-consuming and also the way which requires the most experience, if you download the program and you manually resolve dependencies and you install everything that is needed to run that program. This is not rare. There are so many bioinformatics software even nowadays that will just give you a list, so you can download the software itself, which is an executable, or you have to compile it, so you have to make a binary executable file from the source code yourself. And during this compilation, it will check if you have all the required dependencies, all the programs that are needed to run that specific script. And if not, it will not finish the compilation, and you have to provide all these dependencies one by one. So here is this word dependency. In many cases, we are using this, and this is one of the most important things you have to understand when you install a program on a Linux environment. So what is dependency? Let's get one of our lab examples, which is the Tradis. So just as here you can see a small figure on what actually Tradis do. And if I'm saying something wrong, please, those guys who are really doing Tradis, just correct me. But actually what you are doing, you have a big bunch of bacteria, and you shoot them with a plasmid that will go into the bacterial cell and incorporate into the genome randomly. So at the end of your transformation, you will end up with a library of bacteria where each cell has one random insertion event somewhere in the genome. Of course, there will be genes that cannot be destroyed. Of course, each insertion event is probably knocking or potentially knocking out that gene. So first of all, you cannot really knock out those genes which are essential for surviving the bacteria. But the main purpose of this method is to check if there are essential genes for specific microenvironments for the bacteria, or specific nutritions, for example. to survive. And what you do is that you also grow your library, or inoculate your library into different animals or different conditions, and check what are those gene knockouts which are not surviving in these conditions. And then you have a bioinformatics pipeline, and that's here at the bottom, where you compare your original library with your library, with your sequencing coming out from your testing environment. And there is a pipeline, which is called BioTradis, which do this very nicely. But as soon as you are going up to the BioTradis GitHub website, you will see that it is depending on many other tools. So instead of writing a new short read aligner and the tools to transform next generation sequencing file formats, and writing a new programming environment and writing a lot of functions in programming to deal with bioinformatics data, they just build a layer above already existing programs, and that's actually the dependency. The BioTradis cannot work without these programs. These has to be installed if you want to run BioTradis. In an ideal world, you don't realize that they are there, because if the bioinformatics software has a good installer, for example, a Conda, or it is already in a Docker image, you won't realize what you are using, but you have to know that these programs are somewhere there in the background. It has to be on your computer. And I will tell you soon why this is very, very important a bit later. So what are the initial problems with dependencies? Of course, you need all of them to run your applications. That's why they are dependencies. But you also need the dependencies of your dependencies to run your applications. And you also need the dependencies of the dependencies of the dependencies of the dependencies. So up to, so as soon as you are starting building up dependencies, the top level can be like 4th or 5th level up, and you have to have everything that is below that top level of dependencies. And this is only the software dependency. I will speak about other dependencies very soon. The problem is that if you think, okay, this is a Python script, what you want to run, for example, BioTradis. I think BioTradis is a Python script as far as I remember, or it's a collection of Python and R scripts, which should work on Windows, on Mac, working perfectly. So it's okay. Then I can run BioTradis on my Mac, or I can run BioTradis on my Windows. But if you look at the dependencies, for example, SemTools is not really, there are a few translations from SemTools, also BWA to Windows, but it's actually working way much better on Linux, and it's also much more updated on Linux. So your dependencies can change the way how you can, what you can use as an operating system or as a hardware. Another good example here with dependencies, if you think about what BioTradis scripts do, then you can think that, oh, that's just comparing two tables and do some extraction of data. That doesn't require too much CPU and memory. But if you look at what is behind, again, what are those programs are using that are working in the background, BWA, for example, is requiring a lot of CPU and a lot of memory sometimes. It's, of course, depending on your reference genome size. So you have to be very careful and have to know about the dependencies. Don't try not just to jump over the dependencies. Even if you install something with Conda, and which means that all the dependencies will be installed. Just look at that section, which is about the dependencies, and try to read about those programs, those applications as well, a little bit. What are the requirements of those applications? A very huge problem with the dependencies that if there is a bug, there is a software bug. So the bug means that in special circumstances, the program will stop working or will do weird things. Then the creator of the final software will not, actually cannot fix it. Let me show you an example. I'm using this program, this GTDBTK, which is actually the extended version of Checkm, which is a program to taxonomically to identify a taxonomy of a bacteria, of an unknown bacteria. So if you have an assembly, but you don't know what is that bacteria, then you can try to identify it with Checkm. You can also do quality measures on your assembly, the length of your context and other parameters with this program. And GTDBTK is an extended version of this, very useful. But it is, as you can see, again, it is depending on many things. It is depending on a few Python libraries and also depending on other bioinformatics software. One of them is pplacer, which is a very good phylogenetic tree building program. But there is a bug in this pplacer. If you are running it on an HPC, on a high performance cluster, then it can misdetect or can have problem with detecting the memory amount in that computer. So it actually thinks that it has much more memory than it really has. So it starts using that huge amount of memory, which is not there, and your program will just queue it because it will go out of memory. The issue was realized quite early with the GTDBTK, and it was reported in the GitHub site. There is a problem with this software, with the GTDBTK, because on HPC, it in a special circumstances, it's actually not that special. I had the same problem with this program. It's very easy to reproduce. It will stop working. And then there was really a solution. As you can see here, it's the issue is closed, but it's not really solved. It is solved if you have your in-house server. You just have to put in more memory, and it's solved. But on the HPC, you have to do some wizardry. So you have to allocate more memory that should be allocated per CPU. So what I'm doing actually at the moment is that I'm running the program by asking the memory for 24 cores, 24 CPU cores, but I'm only running the program on 4 CPU cores, because on an HPC you usually get the memory together with the CPU. So it has to be almost like hacked to get it work. But the main thing here, what I wanted to show you, that the developer of GTDBTK is not capable to do anything in this case, because it's not his program which has the bug. It is the pplacer. And as you can see, the pplacer, the reference is from 2010. So probably that was the last time when the developer touched the pplacer program. And from that moment, there is no one who will go back and rewrite the code and repair this bug. So again, this is a problem with dependencies. The version control is very important. The sign what you see here is equal or more. So what you see again here, you may saw these signs here, which means that the developer of this program, which is the GTDBTK again, knows that the HMMR or the Prodigal or the pplacer is only working together with this program if it is at least version 1.1 or more, version 3.1 or more, version 2.6.2 or more. That's important because if you already installed HMMR, for example, which is the hammer, it's a PDM Markov model program, but you installed an earlier version, then it won't be enough for this program. So you have to reinstall, or you have to create a microenvironment again, for example, with Conda, where you provide the good version of HMMR for this program. In many cases, but not all of the cases, you can see the versions. But for example, Bioinformatics does not really care about versions. You don't see anything which SAM tools, at least which version of the SAM tools you should have, at least which version of Smart you should have. But this can be a problem. New versions can cause problem too, and this is very rarely mentioned in any installation. They are just saying that, okay, this kind of feature, what my program is using from that application, was introduced in version 1.2. So you have to use from SAM tools, from BWA, at least version this one or version that one. But the problem is that as these programs are evolving, sometimes features, most of the times, new features come in. But sometimes features will be deleted or just excluded from, or just simply altered in these programs, which means that there will the backward compatibility will be changed or disturbed. So in these cases, you can have a problem or a running problem with the new versions as well. Of course, you can ask me why should I install a new version of SAM tools if, okay, let's say that I installed GTD-BTK and it works perfectly. Then why should I update my fast tree, or why should I update my mesh? As it's working well. It's very rare that you are going back to a working bioinformatics program and try to update the dependencies. You should never do that. But it's very common that you are installing a new bioinformatics program, which is depending on mesh as well, but it's depending on mesh 3.0, not 2.2. So you are actually overwriting your mesh if you are not careful. You can, of course, preserve both versions. So let's make the picture even more complicated with the different levels of dependencies and what you have to be. So you have to be very careful with dependencies. So I have 4 levels here, and I will go through each of them, and I will tell you what you can do to avoid problems with dependencies. So of course, everything is depending on the hardware. That's what we spoke about a week ago. You have to have enough memory, you have to have enough storage space, you have to have a good enough CPU to run your programs. Then a lot of things is depending on the operating system. The operating system is that layer which connects everything. It creates the communication between hardware and everything else. And then there are 2 sub layers before your bioinformatics application. There are the environment. I'm not sure that everyone splits these 2, but I think it's important. So there are the environmental dependencies, and I can give you an example here. Again, going back to Bioinformatics. And there are the coworker applications. So what I'm calling coworker application is, for example, PWA, Smart, SAM tools, or TABIX, which is there for for reading in the data, doing something on the data, and creating an output. So your bioinformatics application is not really communicating through these applications with your operating system. It is just using there as a step in your pipeline, giving an input for the BWA and taking the output of BWA. But it's not communicating through the BWA. But in the meantime, you have R here. R is a programming language, is a programming environment. So if you have, and I'm sure that the BioTradis has R scripts built in. The R scripts will be compiled real time by the R programming language environment and will be sent to the operating system and the hardware at the end to do something on the computer. So that's why and Bioconductor is actually a huge R package to provide a lot of functions for bioinformatics works. So in my mind, the coworker applications are only there to take up a few steps or help your final application to do something what is already written, and you don't have to rewrite these things, and they are complete packages. But when you are doing real programming, then you are communicating through some kind of environment, most commonly some kind of programming environment, which can be an R compiler, Python compiler, a Perl compiler, or any other kind of programming language. So what is happening if you have problem with dependencies on any of these layers? Let's go again from bottom to up. So if you have problem with your hardware, there is almost only one solution. You have to replace or you have to extend that hardware component. There is a very limited way to trick the computer and say, oh, actually you have 8 CPU cores, not 4 as you think. No, you cannot make 8 CPU cores from 4. You cannot make more memory if you have some. Last week we spoke about RAM drive and swap space, which is a kind of extending the storage space or extending the memory. They are only emergency solutions. You cannot rely on these solutions in long term. Long term, you have to open the case, take out that hardware component which is not good enough, and put in something which is better. The next layer is the operating system. You have actually 2 choices here. You can make a multi-boot computer, which means that when you turn on your computer, not from sleep, not from hibernation, but from the turning off state, instead of starting an operating system right away, you will have a choice, a small window with choices, and you can choose operating system 1 or operating system 2. The most common way to do a dual boot operating system computer is to install a Windows first on the computer and then install a Linux, because Linux can handle multiple boot. If you install Linux first and then try to install Windows will just simply overwrite Linux. It doesn't want to be on dual boot computer. So you have to first install Windows and then install Linux. And when you're installing Linux, there will be a question if you want to completely erase your computer or you want to make it as a dual boot system. So when you turn on your computer, you can choose between Linux and Windows. And if you choose Windows, you will have only Windows. If you choose Linux, you will only have only Linux. They are not running at the same time on the same computer, which is good in terms of resource sharing. So they don't use the CPU together. They don't use the memory together because there is only one operating system running at a time. So that's a good thing with dual boot. the problem is that because they don't communicate, they don't see each other's space usually. So if you like using as a workstation Windows more, and you have your email on the Windows, and you like browsing on Windows, and you like downloading things on Windows, but you like doing bioinformatics on your Linux, then you have to boot into Windows, do all these things. If you want to share something, you probably have to put that file into an external drive, and then turn off the computer, turn on again, off and on again, and start the other operating system, which, for example, the Linux, and then read in the things from the external drive. So because they are don't running at the same time, they don't communicate with each other. There are hardware issues with Linux, which has a much smaller problem with virtual machine, which is the second option you have. So there are many hardware components, especially new ones, which won't be recognized by Linux. So it's sometimes a bit hard to work with Linux and special hardware, which is also a problem with dual boot machines. Okay, so the other option you have is the virtual machine, and this is what I asked from those people who actually has a Windows machine, just to have a proper command line, Linux command line. You should install a virtual machine, which means that you are actually running two operating systems side by side. You have a host operating system, which is usually the Windows, and then you are running a completely separated Linux inside. They can, because they are running at the same time, they can communicate with each other, they can share files, folders, but they also share resources. So if you need all the CPUs, if you need all the memory for your Linux application, then it's not good to have a Windows 10 in the background using 2 GB of RAM, using a lot of CPU. This has to be keep in your mind. But if you have enough resources, then you can just do your work in your original operating system. You can do your workstation tasks, and you can use the embedded Linux operating system as your bioinformatics environment. There is also a bit less hardware incompatibility here, because the Linux is not really handling the hardware devices. The Linux is handling an intermediate layer, which is the virtual machine program. The virtual machine program provides virtual hardware to the Linux, in this case. There is a 2.1 layer on the operating system. So there are cases when your dependencies are not other bioinformatics software, but some core operating system components. That's the easiest case, because if you are relying on something which is already included in the Ubuntu distribution, then you just have to install them with the Ubuntu package manager, which is very easy to use. It's one line of command. Of course, you have to be a super user to do this. So you have to be the administrator of your computer, which if it's your own, you are. But this is a very easy way to solve dependencies if they are core Linux packages. The next layer, and this is the layer which you will deal the most, is your last layer before your bioinformatics application. So all the environmental dependencies and all the coworker applications. You have three main choices. Each has its advantage and disadvantage. You can create a separate whole working environment for this application, which means that everything will be packed in an image which will be invisible from outside. which no other program can alter. So it will be a perfect environment. Usually this is provided by the software developers. You don't have to create this, you just have to download and use it. And this is what Docker do. So it's a very safe, very permanent solution. But again, as I told you before, nothing is shared between Docker images. So if you want to try 10, 20, 30 different bioinformatics programs and you are building up a Docker image for all of them, you will run out of space on your storage device very quickly. The other option is to install all the dependencies automatically again with the Conda package manager. This is very useful and very easy to use. And as you will see at the end of my presentation today, this is the one which I recommend the most. Try to use Conda if it is possible. The only thing you have to be very careful with Conda. So first of all, the good thing is you don't have to be an admin, a super user or administrator. You can use Conda as a user with just simple user permissions. You can use Conda on HPC as well. You cannot use Docker on HPC. For example, Docker is not installed. You are not allowed to install Docker because you have to have administrator rights. So the Conda is okay, but because you are installing it as a user, that means it will be only a micro environment for you. So as soon as you want to share your programs, your pipeline with someone else in your group or with someone with your collaboration partners, even if they are using the same PC, the same HPC or in-house server, they have to reinstall everything and build up their own environment as you have to do it. So you don't have to, it's not enough just to give them, okay, run my pipeline with this line, but you have to write down them that if you want to run my pipeline, you have to first install this like that, and this like that, and this like that, and then you can run my pipeline. And the last thing is, which is common, which is of course the most time consuming and requires the most experience, is to install everything manually. There are advantages to install things manually. If you can ask, for example, the administrator of your in-house server to install SAMtools, then you don't have to install SAMtools, and your colleague doesn't have to, and your collaboration partner doesn't have to install SAMtools because the admin can install SAMtools centrally. So everyone can use SAMtools from that moment. It will be there, hopefully that version, which is good for all bioinformatics programs. And this means that even if 10 or 20 or 50 people is using that in-house server, the SAMtools will be there only in one copy. So there are many advantages. Also a good thing in installing things manually, especially if you are compiling it from source, that you are using those compiler programs which is the best for your Linux distribution. If you download something which is pre-compiled, so which is already executable, then it was probably transformed. The compilation is when you are transforming your human readable program code to something which is computer readable. The two things are very different from each other. And transforming a human readable to a computer readable format is what we are calling compiling. If you are doing Python codes, Perl or R codes, you don't really see the compiling when it's happening. But actually what is happening is when you run your Python script, there is a microsecond or a half second when your whole programming code will be compiled on fly, and then the compiled machine or computer readable format will be executed. And if you are compiling your source code to your binary in your own server or computer, then it will use all those environmental libraries and programs that are the best for that Linux distribution. So just to make it very simple, it's possible that if you download a compiled binary and you run it and it runs on your data for 2 minutes, and then you download the source code and you make your own binary on your own server, which takes up maybe an hour, but then you will have your binary. And from that moment, maybe you can run the same program on the same data set, on the same server, not for 2 minutes running, but for like 1 minute and 45 seconds, which is of course not a big save. But if you are running the same thing 1,000 times, then it will build up to a significant time. There are some tips how to tackle with dependencies and what to be very careful. For the very first layer, if you have a hardware dependency problem, if you don't have enough memory, for example, it's not always that simple just to replace the memory. The most obvious problem with memory is that if you open your computer case and then you see that there is no more memory slots, you cannot put in more memory. But even if you take out the memory modules and put in bigger ones, there is a good chance that the motherboard, which I spoke about last week, which is the basic board inside the computer which holds all the parts together, the motherboard is not capable of handling more memory. So even if you can buy it, even if the program what you want to use can handle more memory or can only run in more memory, maybe your hardware is not good enough to handle that amount of memory. There are so many hardware and operating system incompatibilities, which again, you have to take into account when you try to resolve dependencies. For example, if you are planning to run anything on a graphics card, like doing molecular modeling on a graphics card, and you have the money to buy the best new graphics card, which will be 10 times faster than what you have in your computer at the moment. But it turns out that you don't have that specific slot, or you don't have a good driver because it's just too new and you cannot really, and the operating system won't be able to recognize that hardware component. Very important to know for these dependency troubleshootings that many solutions requires admin rights. You will never be allowed to put any virtual machine on a server where you are a user. You are not allowed to do core package installations. Only the super user can do this. Also installing Docker. It's very nice that in many programs they provide you a Docker image, but for using a Docker image you have to install Docker first, and for that you need admin rights, not just user rights. As I said before, when you are installing a virtual machine, then your two operating systems that are running simultaneously on your computer will share the resources. So you have to be very careful to allocate more or less resources to your Linux operating system, because you can slow down your Windows very much, or if you don't allocate enough, then you won't be able to do real bioinformatics work on your Linux. So you always have to plan, but you can also alter these settings later. So if you feel that you need a bit more memory and you think that your Windows can work with less memory, then you can allocate more later. So you don't have to reinstall virtual machine. You don't have to reinstall Ubuntu or any kind of Linux for that. As I said before, the microenvironments are not shared between or among users. So if you want to share your pipeline, if you want to share your working pipeline again, then you have to tell the other user how to install all those programs that are there. Because they are not shared, they are using storage space, and that's why I told you that if you are using a program which will be probably used on the same server by other 5 or 10 users, then it's not a good way to use Conda for all the 10 users, build up their own microenvironment, because it can eat up quite a lot of storage space. You can, in this case, you can just go to the administrator of that server and ask to install your program properly, centrally, and then everyone will be able to use the program. This is especially important for those kind of bioinformatics software which has their database built in. For example, the one which I mentioned before, the GTDBTK, is using a lot of data. If you install with Conda, it comes with its huge database as well. If you install 10 times because 10 users wants to use that program, then the same gigabytes of data will be stored on the server, which is, I think you can see it's not efficient. And also, it's very important that programming language environments can be very tricky. The most infamous one, of course, is Python 2 and Python 3. There was a huge version change, so there are program scripts which are running in Python 2. And actually, there are also subversion problems with Python sometimes, and they will never run in Python 3. Or you can make it backward compatible, but it will be slower. And of course, Python 3 scripts will never run on Python 2. So even if you think that, oh, it's Python, it's the same programming language. Yes, but it's 2 different main versions. So you can have a lot of problem mixing up these programming language environments. You have to be very careful. So we are here how to mess up dependencies. Spoiler alert, it's very, very easy to mess up dependencies. The most common cause, if you mess up something, that you install something new. I mean, this is not a failure. You are always trying new bioinformatics applications. You are always installing something which may be a bit better than the other one. And you cannot be careful enough. I mean, if you install 5, 10, 20 different applications, you cannot be in your memory that, okay, the second one I installed is using the SAM tools, but as far as I remember, it is using SAM tools 1.1. So if I install SAM tools 1.0 or 2.1, then maybe something will happen or not. You actually cannot really memorize all these things. Of course, you can have some kind of notebook, you can have some kind of notes about this, but the most common thing is that if you go back to your second installed applications after installing 18 more, that it won't work. And then you have to go back and track back what has happened. So what can you do? I mean, what else can happen? What can be the cause of the problem? So maybe you just change the hardware component. As I said before, for example, if you run things on a graphics card and you use an old program which is using an old type of graphics card and an old CUDA programming environment, which is a programming language for graphics cards, then and then after a few years, you just get a new program and you realize that, or you have that old card there, and for a few £100, you can buy a 10 times or 100 times faster graphics card. You just replace it, but probably it will be too new for the old application. It will be too new for the old programming environment. So while your new program will work and will use the potential in the new card, your old program will not even start running on the new card. If you change the resource allocation on a virtual machine, so you know that you can run SAM tools with 4 GB of memory, but because of some kind of reason, you need a bit more memory for your windows because, for example, you are doing some video cutting or just a huge poster you are preparing, and because it has a huge size, it takes up a lot of memory with PowerPoint. You want to allocate a bit more memory to the Windows and take away from your virtual machine from your Linux, and it will just stop working because it's not enough memory anymore for the SAM tools. So you have to be very careful with your virtual machine. Very, very careful upgrading your operating system. Even if you are upgrading your Mac OS, and this is not updating, it's very important. Upgrading means if you had a Windows 7 and you are upgrading to Windows 10, if you had a Mac OS High Sierra and you updating it, I don't know, to Catalina, which are huge changes, big new versions of the operating system. It's very easy to end up with software incompatibilities, with dependency problems. Even like the EndNote we had stops working if you update your operating system to the newest Mac OS. It is also true for Windows. It is also true for Linux. So be very careful upgrading your system. In the Linux world, there is a good thing that in many distributions there is a long-term support version. So if you download a Linux and you see the LTS abbreviation somewhere on the website where you choose the downloads, then and you really plan to use that Linux for years from that moment, then choose the LTS. So the LTS is a long-term support version which will be updated for at least, I don't know, usually 4 or 5 years. But after 4 or 5 years, you have to upgrade probably. Upgrading, updating the programming environment. As I told you, the most infamous one is Python. If you upgrade your 2.x to 3.x, then half of your programs or most of your Python scripts will not work. Of course, you can try to keep both of them and then use both of them. Very common mistake or problem when you mess up dependencies if you are installing a program or programming environment or software manually. So what you do with Conda, and this is why it is very, very safe to use Conda. If Conda is installing a new bioinformatics application, it sees that, okay, there is a SAM tools already there, which is used by another program, but for this new application, I have a different version of SAM tools. It will install a different version of SAM tools for that program. So it won't change the versions. But as soon as you are installing something manually, it can rewrite that old version, or it can just rewrite the path, how you can access to that program, and your old software will start using the new manually installed version, which is maybe too new or different. Yeah, before the last one, accidentally, you can easily delete crucial folders and files. The problem is if you use Conda, you don't really see what is happening. It's, I think, no, it's not here. It's one line. You only have to copy and paste one line from the software developer website. This is how you install Conda minus blah, 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 blah. you run this. Of course, there will be a lot of information on your screen, but you don't really care about it. You just go and drink a cup of tea while the installation is happening. And then, of course, you forget all of these things, what happened. But it's actually copying, downloading, and installing a lot of things on your storage space somewhere. And then after a few months, you go back and say, oh my God, I'm starting running out of space. Let's see what kind of folders I have in my home directory. Okay, I remember to make this folder. I remember to make this folder because this is important for this project and this is important for this project. But this folder, I don't remember to making this project. Let's delete it. And there's a chance that it was actually that folder which contains your downloaded program files and dependencies. So with just one a movement, you deleted all your dependencies and your programs will never work again. Of course, you can reinstall them, so that's a good thing. And the very last one thing is a third-party reasons. And I already mentioned that sometimes big programs are evolving as well. Some tools evolved a lot during the last few years. I think it's already over the big version 2. So there can be differences between version 1 and 2. And that's why I said that it's not always the best to install the newest version. I think the most safe is to have that version, which is the one which was included in during the development of the software as a dependency. But also, there can be changes in program inputs and outputs. There can be changes how these programs communicate with other programs. So it's not really the program that changed or how the program do what it does, but maybe in the tabular output, there is a new column somewhere which gives you a new information, but you didn't prepare your whole pipeline to handle in your outputs and inputs that way. It will mess up your dependencies and pipeline again. So I think this is my last slide. Yeah, it's about how to decide which one you should use. In a few cases, there are multiple choices you can choose if you want to compile the program, if you want to use Conda, if you want to use Docker or other solutions. But this is it is quite rare. Most of the times you don't have any choices. You have one choice, you have to do that. But even if you have more options, that doesn't mean necessarily that you can do it. As I told you before, if there is an option for Docker installation and there's an option for Conda installation on the HPC, you cannot do the Docker because you don't have the rights, you don't have the permission to do that Docker installation. Again, you have to plan forward. So if you know that, okay, I'm now building up a server and my whole research group will work on molecular dynamic simulations, 10 people will do the same thing in a huge amount of data, then you want to dedicate that server to that purpose. You want to install the program centrally. You don't want the users use their own versions. You want that all your group members will use the same version, use the same kind of approach to answering the question, and you provide the bioinformatics software centrally. The other case is when you are just simply doing bioinformatics and you want to try this one and try that one and try that programs, then it's way much better to make your little mess in your own home directory. Don't mess up with other people programs. So this is why you have to do, what you really want to do on that server. If you have the administrator rights, for example, if you have your Linux on a virtual machine, think twice or at least 3 times every time you are using sudo. We will probably speak about sudo a bit later. So that's the super user command in front of any other commands. With that command, if you have the permission, and because you installed Linux, you have the permission, you can do everything. You can do anything on your Linux, which is sometimes very dangerous, of course. So just memorize this one thing. If you do something as an admin, be very careful. If you have a chance to discuss alternatives with the admins, do it. If you work on the Hammond server, come to me, discuss if I can install it centrally, if I can help making it faster. If you are working on the HPC and you think that your program would be very useful for the people, you can ask the HPC guys, and they will make a module from that program which you can use as a centrally installed program. Sometimes try to compile programs. As I said, sometimes you can have better performance. Always plan in advance, especially if you have virtual machine, but also if you are just on a server. Try to plan what will you do with this software, what will you do with this package, if you want to share, if you don't want to share, if you just want to try. So think about these things. Stay home and be safe with the Conda. Yeah, in most of the times, it's very safe to use Conda, to be honest. And also, it's a good thing to learn how to use GitHub. That's why I actually linked a GitHub video as well. It's very good in many purposes. You may not use it as for that purpose what it was created to in originally. So GitHub is very good if you want to develop programs together with someone else. It's very useful. But also if you just download things from GitHub, if you try to solve problems on GitHub, it's very useful. You can raise issues. If you found a bug, you can raise issues. It will be answered probably by the developer. So be familiar to use the GitHub. So that was all for today, and I'm very happy to discuss and hear your thoughts and hear your bad or good experiences with installing programs.